This is CE board November of 2025. A load W is to be lifted using the crane which is hinged at B as shown in the figure. The value of X sub 1 is 8 meters, X sub 2 is 4 meters, and H is 9 meters. Number 1. If the weight W is 24 kilonewtons, determine the total reaction at B, neglecting the weight of the boom. So the weight is given, you will find the reaction here. Number 2. If the allowable tension of the cable AC is 48 kilonewtons, find the maximum value of W, neglect the weight of the boom. And number 3. If the boom weighs 8 kilonewtons and the allowable tension of the cable AC is 50 kilonewtons, find the maximum value of W. Let's start with the total reaction at B. So here's the figure again. For number 1, you need to find the total reaction at B, not just the vertical and horizontal components of the reaction, but the total reaction. And first, let's look at the entire figure here. You will see that the boom BC is an actually loaded member. And in this case, it will be in compression, like this. So these are the forces in the beam. This one is pushing through the joint C, and this one is pushing towards the pin. So if we are going to remove the pin here, that will be replaced by a reaction that is opposite in direction of this force here, like this. Let's call that RB. This one here is the weight. Let's call that W. Again, the direction of RB will be in the direction of the boom, or it is collinear with the boom. So that means we'll be able to determine the angle it makes with the horizontal or the vertical, since we are given these dimensions here. This one here is X sub 1, which is 8 meters. This one here is X sub 2, equal to 4 meters. And the height H equals 9 meters. B, C, and this point here will form a right triangle. And then here, A, C, and intersection here will also form another right triangle. And since the sides are given, we can solve the angle by using the trigonometric function tangent. Tangent is opposite over adjacent. Let's call this angle alpha, and the other one is the angle at B, we call that angle beta. So to solve for alpha, that is alpha is equal to arctangent of opposite side is 9 or H. The adjacent side is the total of x1 plus x2 or 12. So it's H divided by x sub 1 plus x sub 2 equals. This is in radians. Then beta is arctangent of the opposite side is still H, but the adjacent side is now x sub 2. X sub 2. And this is equal to 1.153 radians. We can convert this to degrees, but it doesn't matter. Okay, now we can use summation of moment at A to solve for RB. We can resolve RB to its vertical component here and horizontal component here. And we will be using only the vertical component, which is, in this case, opposite the angle beta. So that's RB sine beta. Or we can do this. We will find the moment arm of RB from A. So we need to extend RB, or the line of action of RB, like this. So this is the line of action of RB. And then we'll draw a line from A perpendicular to the line of action of RB. So this 8 meter is this one. This horizontal line here, AB. That's 8 meters. Let's move this over here, and this angle will be the same as this angle beta. That's beta. Okay, since we have beta and we're given one side of the right triangle, that means we can solve the other sides and the other angles. So what is important here is this side of the right triangle, because that will be the moment arm of the reaction RB. Let's call that distance D sub 1. Okay, to solve D sub 1, this D sub 1 is opposite side of the angle beta, and we're given this side, which is the hypotenuse of the right triangle. So this one is the hypotenuse times the sine of the angle beta. So D sub 1 equals X sub 1 times the sine of the angle beta equals 7.31 meters. So now we have the moment arm for RB. The moment arm for W is just the sum of x1 plus x2. So therefore we can proceed with summation of moment at A equals 0. Considering clockwise moment as positive, so we'll start with this one, W. It will create a clockwise moment at A. So that's W times the moment arm will be the sum of x1 plus x2. X sub 1 plus x sub 2. Then this RB will create a counterclockwise at point A. So that's minus R sub B times D sub 1 equals 0. To solve for RB, R sub B equals in kilonewtons. That's 39.395, or this is 39.4. Let's see. 39.4 is letter A. This one. Letter A, 39.4 kilonewtons. Number 2. If the allowable tension of the cable is given equal to 48 kilonewtons, what will be the value of W? Neglect the weight of the boom. Okay, so number 2, let's start here. Okay, so what I'll do is I will cut this cable here. So if that cable is being cut, that will be replaced by a tensile force, like this. So this will be TAC, and this is our unknown W. So we are going to find the value of W given T sub AC, or the tension in the cable AC. So according to the problem, TAC is 48 kilonewtons. So this one is equal to 48 kilonewtons. To solve for T sub AC, we can project this one, draw the line of action of TAC up to point A, and then we will resolve TAC to its vertical and horizontal components. And then sum up moment at B using the vertical component of AC, then we'll be able to solve for W. Or we can do this. After we project the line of action of TAC, we'll find the distance from point B to that line of action. This one. So this is the line of action of TAC going to point A, and then if we are going to draw a line from point B perpendicular to the line of action of T sub AC, then this line is the moment arm of TAC when we are summing up moment at B. Let's call that distance D sub 2. Now we know that A to B is x sub 1 or equal to 8 meters, and we already have this angle alpha here. So this is angle alpha and this is x sub 1. So using this right triangle here, we can solve D sub 2. D sub 2 is the opposite angle of alpha. X sub 1 is hypotenuse. That means D sub 2 is x sub 1 sine of alpha equals 4.8 meters. So this is 4.8 meters. X sub 2 is given. That's 4 meters. So we can now sum up moment at B. Summation of moment at B equals 0. Clockwise moment as positive. By the way, this is W. That's the unknown W. So our equation is W times the moment arm x sub 2. That's clockwise moment about point B. This one will create a counterclockwise about point B. So that's minus T sub AC times D sub 2 equals 0. So we will be solving for W. So W equals, in kilonewtons, that's 57.6. 57.6. Number 2 is 57, this one. So letter D, 57.6. Number 3, if the boom weighs 8 kilonewtons and the allowable tension of the cable is 50, find the maximum value of W. So it's just similar to number 2, except we have an additional force, that's the weight of the boom, and the tension becomes 50. So here is the figure again. Our TAC is 50 kilonewtons. Our weight of the boom, let's call that W subscript boom, is 8 kilonewtons. So this is what we need to find, W. This one here is the weight of the boom, and T sub AC here. We also need the distance, D sub 2. This one, the moment arm for TAC. Moment arm for the W sub boom is just 1/2 of x sub 2. We know our x sub 2 is 4 meters. Okay, so we'll do summation of moment at B equals 0. Clockwise moment as positive, that's W times x sub 2. Another clockwise moment will be that of the boom. So plus W sub boom times the moment arm is 1/2 of x sub 2, or x sub 2 over 2. And then the moment TAC times D2 will be counterclockwise, so that's minus T sub AC times D sub 2 equals 0. So our weight is equal to, in kilonewtons, 56 kilonewtons. That's letter C, this one. So our answers are letter A, 39.4 kilonewtons, letter D for number 2, 57.6 kilonewtons, for number 3 is letter C, 56 kilonewtons.